Hello everybody, and welcome to part 4 of exercise 1. We're looking at page 16 here in the workbook. And this is another example where they're giving us a vector space. Okay, in this case, C of R, the set of continuous functions from R to R, and they're asking us whether or not this subset, W, is a subspace of V. Okay, so this kind of refers back to a previous exercise. So in part 3, you actually show that C of R is a vector space. Okay, so we're kind of using that knowledge from part 3, that the set that we're starting with, in this case V, is really a vector space. And the question now is if this subset is also a vector space. Okay, well, what does W look like first? Well, it's the set of all functions that have the form mx plus b. Do you recognize that equation? That's really just the equation of a line. So we're asking the question, is the set of all linear functions a subspace of the set of all continuous functions? Okay, well, as usual, we're going to use the tool, theorem 1.3. That's kind of our standard tool anytime we want to answer a question about subspaces. Okay, so we'll run down the properties one by one. So starting with the question, is the zero vector contained in this subset W? Okay, well, what is the zero vector in our vector space V? It's just the function f of x equals 0. Notice that we can produce that function by just choosing m and b both to be 0. Okay, so let's make that observation. Okay, we see that if we do that, if we choose m and b both to 0, this right-hand side collapses to 0, and we get the 0 function. Okay, so the function f of x equals 0 is in W. Okay, so we've just verified the first property of theorem 1.3. Okay, what about the other two properties? Well, those were about closure under addition and scalar multiplication. Okay, so let's start by taking any two functions that are in W. I'll use the letters f and g since we're talking about functions. Okay, and any scalar c. All right, and first question is, if f and g really live in W, what form do they have to have? Well, the definition of W is everything in W has to look like a linear function. Okay, so we know then that f and g can be written in that form. So f maybe looks like m1x plus b1, and g looks like m2x plus b2. Okay, for some real numbers, m1, b1, m2, and b2. Okay. So, what about the question of closure then? Well, let's look at f plus g. If we add f and g together, we're just taking m1x plus b1 and adding it to m2x plus b2. And the question that we're asking is, if we do that, is the sum in this form of looking like mx plus b, looking like a linear equation? Notice that it is if we rearrange our terms. Okay, we can add everything up and regroup like this. And notice what we've demonstrated then is that that sum f plus g looks like a number times x plus another number. That's the form of a linear function, and so we've just demonstrated that this is in W. Okay, that's closure under addition. Okay, what about scalar multiplication? Well, cf times x, okay, would look like c times what our function f of x looked like. That was m1x plus b1. Okay, and if we simplify that, that looks like cm1 times x plus cb1. And again, the question, does that fit the form that it needs to live in W? It sure does, okay, because it looks like a number times x plus another number. That means that that scalar multiple of f is in W. And we've just proven closure under scalar multiplication. Okay, so if you look back up at what we did, we just verified all three of the properties of theorem 1.3, and therefore, by apply that theorem, W is indeed a subspace.